Good evening. My name is John Dickey, and I did my engineering disaster project on the Therac 25. All right. First off, what is the Therac 25? It was a radiation therapy machine introduced in the mid 1980s. It's very infamous, being one of the most tragic software disasters in history, and the story is very central to the field of safety critical software engineering. The initial goal for the Therac 25 was to deliver controlled doses of radiation to cancer patients and was considered an advancement compared to previous designs, those being the Therac 6 and the Therac 20. The Therac 25 sought to replace hardware safety interlocks with software controlled safety systems, reducing mechanical complexity and cost. It allowed dual modes, electron beam and X ray photon, in one system, giving clinicians flexible treatment options. And it also improved precision and efficiency of treatments by relying heavily on software automation. All right, and as you can see on the right, there's a photo showing a very generalized image of how the Therac 25 was set up. You have the computer with the software, and then you have the main base of the body, and then you have the light source, the X-ray source up top right, and then the little dotted lines right there is the movable tungsten screen, which would allow the doctor to be able to switch back and forth between the electron beam and the X-ray photon modes. The reason why the Therac failed. Therac 25 caused at least 6 known radiation overdoses between 1985 and 1987, some of which were fatal. There were multiple factors that played in this failure of the Therac 25. It relied way too much on software and eliminating hardware interlocks, the safety nets. Engineers believed that software could reliably handle all safety functions. The Therac 25 also reused old codes from its predecessors. And engineers that put the codes in didn't think to update the code because the code was based off the hardware interlocks. The existing code wasn't created to be the only defense mechanism, basically meaning that it didn't have any ways to counteract things that might have been able to be stopped with the hardware interlocks. The old code also wasn't really tested in the new Therac series, meaning that the code was very much, they kind of already trusted the code based off of the previous predecessors and didn't think to go through and retest it to make sure that it still worked the same on the new software or the new component. User interface and human factors. Operators were uploading code to the Therac 25 much too quickly. This prevented the Therac 25 to accurately process the information being given, and it skipped over any safety checks that it would have otherwise caught. The Therac 25 also didn't give a clear indication whether the machine was active or idle, meaning that when, like if a doctor was just sitting, getting it to quote unquote warm up, it would actually be active, and so the doctor would not be paying attention to it and sometimes could misfire. And then finally, the organizational and regulatory gaps. There was no mandatory safety review manual for medical device software during the time of the Therac 25, so the 1980s. Reports of overdoses were often dismissed as operator error, making the response to the problem delayed. The manufacturer, AECL, was slow to acknowledge the software was the root cause, and going back towards the operator error, they were also afraid to admit that, to take the blame for the problem of the codes. Some ways to prevent the future failures of this engineering failure was having hardware interlocks plus fail-safe defaults. Keeping the hardware interlocks obviously means that there's more control for the operator. They don't rely too heavily on the code. And having fail-safe defaults also allows the code to be more prepared for any undesired results. Software engineering, just making sure the code that they put in works, doing multiple tests over them, getting different conditions and seeing how one factor plays against another, and then documenting, excuse me, the results that they get from each test. Human factors, you have unambiguous UI, which makes it just able to be read correctly with no confusion. Um, Having kind of mentioned in the previous bullet point, guardrails against operator error. It gives it gives a safety net basically for any problems that might occur through the code due to like a loading error that the operator put in. And then having the Therac 25 or whatever the future one is created to be called, have it give messages when something goes wrong so that the operator actually knows that something went haywire in the code or whatnot. You got oversight reporting, which is just reporting. You would think that's kind of a staple point for stuff like this, but making it prominent that you report what any issues that happen and continuously monitoring the tests to make sure that nothing goes wrong during them is definitely something that engineers and doctors can work on. And then finally, you have culture and training, basically just making sure that everybody who operates one of these is trained to prioritize the safety over cost and speed, and making sure that everybody is trained together so that there's no confusion on how to operate the machines in the future. So in conclusion, the Therac 25 disaster wasn't caused by a bug. It was a result of systemic failures in design philosophy, testing, oversight, and human-machine interaction. This engineering failure teaches that in the future, if relying on software in the safety critical domains, medicine, aviation, nuclear, and automotive, software must be treated as a potential point of failure, never the sole guardian of life. Designing with redundancy, transparency, rigorous testing, and accountability ensures that the noble goals of innovation like curing cancer don't get undone by preventable tragedies. And then these are my sources. This was a case study by the University of Texas on the second one. This was just, I want to say it was a documentary or a project that I just found online. And then ChatGPT helped me format the slides, change the words a little bit to make it more formal. And thank you for listening to my video. And this was the engineer failure of the Therac 25.